My guest today is Joseph Fournier.
Well, thank you very much there, Tom. I've been a fan of your podcast, and I try to keep abreast on all the new ideas that are coming out in the field of climate science and alternative perspectives. So I'm glad today to have the opportunity to talk with you and present to your audience. My background, I am a private sector research scientist. About 15 years ago, I moved into environmental sciences in Alberta, Canada, and then into Alberta's oil sands industry for a good 10, 12 years doing technology development, research and development in mining reclamation and energy production. The last few years, I've sort of hung up my spurs from the oil sands sector and been ranching since about 2020. I've been a full-time sheep rancher. Here, just about 100 kilometers east of Calgary, Alberta, and I've been taking up active writing opportunities with the Western Standard, and also been working with a good friend and mentor named Dr. Henry Mason from France, who's just an amazing statistician and physical chemist. We're doing research as well on ENSO-related climate phenomenon. So what you're going to see today here is just a bit of a snapshot into some of the areas that Dr. Mason and I have been working for the past 5 or 6 years. Hopefully later this year, we'll have our first publication, and hopefully a few more after that. So today, the topic is what I view as a gap in mainstream ocean carbon cycle models. This here is an illustration I created simply due to the fact that I have been struggling for a number of years to find any type of representation that I feel that holistically brings together all of the information that we know in terms of modes of interaction between the ocean and the atmosphere, and natural versus anthropogenic influences. So as you can see here, the title is more or less conveying the fact that I believe that the lithosphere is and the geochemical exchange between the lithosphere and deep water in the oceans is where the gap resides. And likewise, on the left-hand side, you can see I've broken up this illustration into latitude versus altitude or depth, altitude of atmosphere or troposphere in the top left. In the bottom left, I've got depth of ocean. You can see the downwelling at higher mid-latitudes and the upwelling in the tropics or equatorial zones. I put in some nice little cartoons there to represent hydrothermal vents and volcanic activity. On the far right, you see I've got concentration on the vertical and concentration on the horizontal extending right, and the same y-axis as the illustrations on the left. You see I've got the concentration of tropospheric CO2 in the top right-hand corner, and down below we've got the isotopic ratio, the delta CO2, that's your isotopic ratio for carbon-13 to carbon-12 in the ocean, showing that it goes towards more negative values as you go deeper. I'll get into that later, as well as it shows that the surface is depleted in the total dissolved inorganic carbon content. So this illustration is a lot to pack into there, but I'm now going to start, as I advance into my presentation, I'm going to start to unravel some of these things. And I will point out before I sort of proceed that what I'm going to show you is actually quite aligned with a significant body of research and publications already. The only thing that really differs is that I'm really starting to emphasize the role of mid-ocean spreading zone seismic activity as like a proxy for the rate of geochemical exchange. You've had Dr. Arthur Littner, I believe his name is, on. And I've been talking with him a little bit and showing him some of my work. And I think there's some synergy there between what he's been doing, what I'm trying to emphasize today. So before I roll on, the bullet points, I've already covered the first one. The second one is when you look in the literature, there is an amazing range of estimated time scales for the rate of bottom water transit time. Bottom water transit time is basically, it's the length of time that deep water spends transiting the bottom of the ocean from the time it downwells, which is the largest zone, is the subpolar North Atlantic region. And we're then following through to where it upwells. And the largest upwelling zone on the planet is in the Pacific, the Eastern Pacific and our tropical zone. The estimates are anywhere from 2,000 to 3,000 years. So that's an important thing to point out, is the range of uncertainty. Moving on here. Here is an example from work by Levy et al. Back in 2013. This is, I'm not going to go into it in great detail, but what I want to emphasize here is this is very mainstream. It shows physical exchange, biological exchange between ocean depths, upwelling, downwelling. You can see the arrows point which direction your organic, whether dissolved inorganic DIC or organic carbon OC, physical transfers, biological transfers. There's nothing in this diagram here that shows, depth of ocean on the vertical and then latitude on the horizontal. The top is your well-mixed surface layer, right? And its depth varies by latitude, i.e. prevailing wind speeds. There's nothing in this model or others like it that indicates that there's any interaction or contribution to this cycle from the lithosphere. It's just a interaction at the ocean atmosphere surface. Some of the highlights from this study that I will highlight is that, in this estimate, which was when Levy et al. Did this work 11 years ago, they were basing their model off of what they said was pre-industrial, i.e. before we started using significant amounts of hydrocarbons and influencing the overall tropospheric balance in the carbon cycle itself. The number that they come up with, which is, I think, important to emphasize, is their numbers suggest that upwards of 300 billion tons of carbonic acid upwells into the mixed surface layer every year. Now, that's a function of atmospheric circulation. So it's not a static value, but the magnitude is very large, particularly considering the fact that this upwelling water in the literature is shown to be supersaturated in carbonic acid. So like popping your beer can or cracking open a bottle of Coke, that carbonic acid wants to off gas the moment you release the pressure. And so, what I find surprising about Levy's work here is that as the small arrows at the very top indicate, only a very small fraction of that is off gas, while over 300 billion tons of carbonic acid is being brought up into the well-mixed surface layer. So with that being said, I'm going to move on now and show why I feel this is actually deficient. So here's some data that actually, Tom, I got, was influenced by one of your other presenters. That I forget the name of the fellow. He did a great job on his overview of ocean science. But the top left-hand one is so important, and it complements the one on the right. So the one on the right is, many people have seen it on Google image search. It shows the path of the meridional overturning cycle, circulation between the downwelling region and in the subpolar North Atlantic region, where then it transits all the way over through the Southern Ocean, along the Antarctic circumpolar currents, and then ultimately it arrives in the North Pacific and then loops around and surfaces along the Pacific tropics and the cold tongue region of the Eastern Pacific. Going to the illustration on the left, you got latitude versus longitude. The colors are this is a dual function of both nitrate, deep water nitrate concentration, as well as carbon-14 isotope analysis showing from the carbon-14 dating, showing the age of the deep water. As you'll see in the North Atlantic, the isoplasts increase in 400, 600, 800, 900. If you follow the path of the overturning circulation on the right, you'll see that the carbon-14 isotopic data suggests by the time that deep water that drops in the forms in the North Atlantic arrives and upwells in the Eastern Pacific, it's over 2,400 years, at least according to this illustration. Likewise, what they find when you look at this, if you sample the water, the deep water along that transit path, the nitrate concentrations rise over time. It's usually explained as being, organic carbon, like algae and fish and whales over the centuries as they fall under gravity towards the ocean bottom and are mineralized by microbes and other life forms, that it leaves behind the nitrogen. You'll find the same thing with other nutrients like phosphates and irons. The bottom water becomes more enriched in nutrients as they move from the North Atlantic over to the Eastern Pacific. So that's the takeaway here is the huge amount of time. We're talking thousands of years for deep water from the point it forms to the time that it upwells in the Eastern Pacific. So complementary here to that slide is this one here, and this speaks to the work that Dr. Wittner has done on correlating current measurements of modern climate change with mid-ocean spreading ridge seismic activity changes over the last 30 or 40 years. The illustration on the left is not from him, it's from some other researchers. And you'll see I'm showing that as you go from the subpolar regions of the North Atlantic and move along the path of the MLC to the upwelling zones of the Eastern Pacific region, the activity of these mid-ocean spreading zones increases from the slowest in the North Atlantic to the highest in along all ridges in the ocean at the Eastern Pacific rise region, or the eastern part of the ring of fire of the Pacific region. I found this very striking when I was starting to study this topic for the detail, in that the area where we have the highest upwelling rates is also right over top of the most seismically active region on the planet, where we have the highest amount of spreading rates currently. Now, going to the Keeling curve, I don't need to go into this much. Most people who are familiar with the topic are familiar with the Keeling curve. Here I've just juxtaposed two different time scales, Mauna Loa versus South Pole. You can see the orbital forcing associated with the seasonal cycle, and you see the out-of-phase characteristics between both monitoring stations. Likewise, you see a higher amplitude in the northern hemisphere versus the southern hemisphere. Now, this is a monthly average time series. When you take this data now and you apply a 12-month rolling average to act as basically a simple low-pass filter, and then you apply a month-over-month difference function to that for both these stations, this is what we found. And I took so it's basically a first derivative is what this is. It's the rate of change, also known as the tropospheric growth rate. I'll call it just TGR going forward for this talk today, just because it's easier to sometimes throw around some acronyms. So the TGR for both stations shows a very strong the El Nino Southern Oscillation, or ENSO time dependence. Now, TGR is in mainstream models and mainstream climate science is supposed to be driven largely by anthropogenic activity. You know, your internal combustion engine and your air conditioner is supposed to be the driving force for this positive imbalance. In the imbalance is source and sink. There's more source active than there are sinks available, so that the concentration rises. And the time dependence of that is supposed to be a function of us and our activities. But instead, we're seeing this very powerful, very clear, positively increasing time series that shows El Nino and La Nina interannual variability. I've got in the bottom left corner there, you just see this is from script CO2. This is just the data showing the majority of the CO2 emissions from humanity is within the middle to higher latitudes of the Northern Hemisphere. No surprise there. That's where most of the land is. However, when you look at the time dependence here between these two time series, they are perfectly in sync. Like there is in temporally, they are aligned. I shouldn't say perfect, but very, very high positive correlation. We'll just see here. Going over now to, here is another complementary time series. This is the from script CO2 again. This is the isotopic ratio, the ratio of isotope carbon-13 relative to carbon-12. I showed the simple equation in the middle of the screen that shows how the math behind this time series. I'm not going to get into this a whole bunch, but the mainstream argument is that the fact that we see the isotopic ratio going towards more negative numbers over time is said to be a smoking gun for the use of hydrocarbons. Hydrocarbons are enriched in carbon-12 isotopes. So the argument is, if it's decreasing, if this ratio is decreasing, going more negative values, it's because that numerator, the denominator in the numerator there in the top position is increasing relative to carbon-12 is increasing relative to carbon-13. Now, for both stations, again, you see the same similar thing. You see higher variability in the Northern Hemisphere at Mauna Loa versus at the South Pole station. And I've shown it at two different time scales to show that they're out of phase with each other. Again, no surprise, because we just find the same thing with the concentration of CO2 for both stations. So again, this shows the seasonal cycle is first order when we're looking at these values, and it's the same physics occurring in both hemispheres. Now, when we apply the same math as I did earlier, where you take the monthly average data and you apply it, the seasonal detrending, which is just that, again, it's just a simple 12-month rolling average, and then you do a first derivative. What we find is, again, well, this is now almost fully detrended. It's just oscillating on either side of the zero axis. But you'll see that when La Nina events occur, the derivative of the isotopic ratio goes negative. And when they see an El Nino, it goes slightly positive. So again, going back to that idea that carbon-12 enrichment is driving the isotopic ratio in the troposphere towards negative values, it suggests that there's something going on when there is a La Nina event, which is a cooling phase in the Pacific tropics, that is the driver behind the interannual variability of this parameter, the isotopic ratio of carbon. Now, I will go on to show this here that I believe the reason why we see this occurring, i.e. the strong negative trend during La Nina events, is that Walker circulation is increasing at a higher rate during La Ninas. Walker circulation, as I'll go on to show you, is the driving force behind pulling deep water from the bottom of the Eastern Pacific to the surface into the well-mixed surface layer, where the carbonic acid that dissolved in organic carbon off gases into the atmosphere. Here's just further data along those points. So I've got some from two separate studies. I've got depth versus total carbon in the top left-hand corner there. And you'll see on its x-axis, it has carbon-13. So the carbon-13 is more positive towards the surface in the literature and in ocean science, because there is pretty much universal agreement on the fact that the terrestrial kingdom, the plant kingdom, enjoys eating carbon-12 enriched CO2. It's a lighter isotope, and so it's more readily taken up into algae and into plants. So when that deep water arrives at the surface, that's enriched in carbonic acid, off gases, and any residual carbon that's in the surface layer is absorbed by algae, or it's pulled out into the atmosphere and absorbed on land. So that's why you see that ratio going positive, that delta 13C going positive within that top 1,000 meters. But as you go deeper, it goes negative slightly. And that they're inverse. The total dissolved carbon dioxide, it is shown to be depleted at the surface, and it's enriched at depth. I show the same thing for a station in the North Pacific, close to the Hawaiian Islands. This work there with John Doerr, 2009, shows that as I'm talking about, the pH of deep water is lower. It's enriched in carbonic acid. And you see that in the DIC, or dissolved inorganic carbon numbers as well. They're inverse. So this is a very important point. And what remains is trying to understand the mechanism behind which this enriched carbonic acid water makes its way to the surface, and how that relates to these first derivatives that I'm showing earlier to start this presentation in regards to the troposphere growth rate and the first derivative of the isotopic concentration of carbon dioxide. So here is just where now I'm combining both time series. Now here is the TGR, or the tropospheric CO2 growth rate, which is a first derivative, versus the seasonally detrended first derivative of the isotopic ratios of CO2. And you see that they're inversely related to each other. When one's going positive, the other one's going negative. And now this here again is I'm evoking what I'm trying to say by showing this data, is that, well, as I just showed, deep water is enriched in carbon-12 isotopes. And it's also enriched in dissolved inorganic carbon, or carbonic acid, particularly. So when you've got La Nina events and you see the TGR, the orange curve, trending positively, you can currently see the isotopic ratio going negative suddenly. And I'm saying it's likely that this reflects that the upwelling of deep water is responsible for both of these inverted time series trends that we're seeing. So here's a study that came out a few years ago. It was Chatterjee et al. 2017 in Science. It was the first major El Nino La Nina transition that occurred, where the recently commissioned OCO2 satellite was able to monitor the progression of this, one of the largest ENSO events in modern history, over the Pacific tropics. So the top left one, the top illustration just shows Walker circulation as under normal conditions. And the bottom one shows Walker circulation under El Nino conditions. Now, Walker circulation is a combination of both your easterlies, wind surface speeds going from the eastern Pacific to the western Pacific. And then you see that steep gradient in the thermocline and the CO2 off-gassing, vigorous upwelling. As those winds are strong, that overall thermocline gradient is steep and you get a lot more CO2 off-gassing. This all comes to a crashing halt largely when you get an El Nino condition because those easterlies collapse. And so this study was very important when I found it because I was highlighting a mechanism behind which I could explain these first derivatives and the seasonal detrending of these carbon-related time series. Here's just a snapshot from his study, their study, where, in the top left, in the top curve, we've got your ENSO indexes. It's the ONI and the Southern Oscillation Index. They're just inversely related to each other because they're just different measurements. One is surface temperature, and other one is the atmospheric pressure across the Pacific tropics. Now, if you go down to particularly the figure C, Chatterjee et al. Is arguing that because upwelling of deep water is decreasing during El Nino events, there's a large reduction in the off-gassing flux rate of CO2 across the tropical sea surface area in the Pacific. And that when you see the transition back towards like a neutral ENSO condition or a La Nina state, you'll see there in figure C, you'll see that the off-gassing goes positive again. So I know this is really, really impactful because, I think there's a lot of people who will also argue that, well, Henry's law says that when sea surface temperatures rise, they should off-gas CO2 because solubility of gases decreases with rising temperature. But this here is showing something different. And it was quite surprising when I found it years ago, even before I started exploring these methods, these data analysis methods. So here's just another data. This is a snapshot data I've gotten from NOAA. So I don't have the source attributed here in my figure, but it's easy to find if you just do a Google image search. Now this just shows flux rate and fugacity, carbonic acid. In the Eastern Pacific, you see the latitude and longitude. You see in a non-El Nino condition, in this case, the data was relative to December 1995 to June 1996. You see both the fugacity and the CO2 flux rates are significantly positive over the Eastern Pacific region. And that when we move into the monster El Nino of October 1997 to April 1998, you find that those values collapse. In fact, these collapse so much that they've actually gone somewhat negative, meaning they're actually absorbing CO2. Let that sink in a little bit. Fugacity is just, think about it as pressure. And, the pressure, the equivalent pressure in the water, just feel like your pop can, super saturated. Fugacity is just a fancy name to say that its tendency is to release to the atmosphere. Fugacity is a measure of that driving force gradient between the liquid and the gas phase. But here's just another study that was done. This is Freely et al. They've done some amazing work in studying this phenomenon. And I'm not going to go into a huge amount of details in this time series because it's a lot. I encourage anyone to look up this paper and study it in detail It's really a powerful story for showing the fact that the Pacific easterlies, the trade winds, is the driving force behind the rate of upwelling of carbonic acid enriched deep water in the Pacific tropics. In this time series from 1982 to 2004, freely shows in the top the sea surface temperatures go positive during El Nino. No surprise. You can see that particularly if you look, take your eye and look from the top to the bottom around 1998, the super El Nino to super La Nina transition that occurred there in the eastern and central Pacific region. You go from sea surface temperature to wind speed, that's your easterlies. You see when sea surface temperature rises, your easterly wind speeds collapse, they decelerate. And when that happens, the fugacity of CO2 likewise rapidly drops. We'll see it in the false color images there to convey magnitude. The flux down below shows that it actually, around that time in the Eastern Pacific, it goes negative. It's absorbing CO2. The Pacific tropics and the Eastern Pacific region, the cold tongue region, it absorbs CO2 during El Ninos. That's what the negative numbers mean. The direction is changing. Going down is negative, going up is positive. So I include this study to show that what I'm talking about is not alternative. For some of your readers your followers who are not as familiar with ocean atmospheric science in this part of the Earth, I'm just going to include some additional background information for showing how deep water upwelling is coupled with atmospheric overturning. Here it shows this, the picture is worth 1,000 words. You can see the overturning cells, the red arrows, they're going in counterclockwise directions and along either side of the intertropical convergence zone, or ITCZ. You see the firebox region, that's the zone of maximum precipitation, maximum evaporation. That is where deep water upwelling is maximum, is along the ITCZ. Now, this is, I think, really important to emphasize, because if you go back to my TGR time series, tropospheric growth rate time series for both stations in either hemisphere, they show that they're almost perfectly correlated in time, yet they're thousands of kilometers apart. This, to me, for anybody who's got a background in pollution dispersion or atmospheric dispersion modeling, it takes time for an area source to disperse and transport over great distances. The fact that we see measurements at two very widely separated stations on the Earth's surfaces showing the same thing, the same temporal relationship, suggests that their area source is shared equally, and that the rate by which the dispersion of gases is coupled in time says, again, it's the area source is the ITCZ of the tropics. Let's see here. I think that should be good. That covered the points that I wanted to cover here. I'm going to move on now. Here's just another classic image just showing how the atmosphere and ocean circulation are coupled in either hemisphere across all the major oceans. This coupling is represented, is often form what's called gyres, and it's due to the coupling of the motion of the easterlies along wind speeds along the equatorial zone, together with the centrifugal forces that develop as the Earth's rotation begins to deflect water and gases into the higher latitudes of either hemisphere. And these gyres are counterclockwise to each other. The the areas where we see the greatest upwelling are along where these gyres collide along the equatorial zones. Here is a wind surface stress vector field for the eastern tropics. And this is the region where we find the largest upwelling of cold, deep water. And that's in the eastern tropics. We often refer to that as the cold tongue region. Now, here is another very powerful image from Donnelly et al. 2006. I think others have been showing this one to emphasize the fact that surface water is, no surprise, the most enriched in carbonic acid in these upwelling zones along the subtropical regions. And as shown here, the Eastern Pacific is the largest. Again, this is due to the upwelling effect of carbonic enriched acid enriched deep water. Here is a very famous study done by Takahashi et al. This is from the IPCC 2007 assessment report, just showing the upwelling of deep water in the tropics. Off-gassing is maximum there. You can see by the red. The downwelling is in where you see the blue and purple there. That is just another representation of the model the representation that I showed in my first slide, where we got the overturning circulation in the atmosphere and the ocean, basically pulling and cycling CO2 through the atmosphere back into the ocean. So where you see it purple and blue, that's where deep water is forming, and that's where that carbon dioxide is being then routed back to the bottom of the ocean. Here's an illustration that emphasizes just how important this deep water upwelling is in the transport of ancient enrichment of nutrients in deep water, how it impacts positively the net primary productivity of the global oceans. I find it interesting that the most acidic water on the planet is also the most productive biologically. A sort of counter narrative to what we often hear in terms of the supposed dangers of ocean acidification, because what we actually find is the opposite to that claim. Here just shows a dynamic effect of the role of upwelling water and Walker circulation during El Nino to La Nina transitions. The top one shows the false color fluorescence from chlorophyll in algae across the Pacific tropics. The top one is during an El Nino state, January 1998, during the chlorophyll concentrations are very low. Suddenly, when that El Nino ends and the easterly wind speed begin to pull out deep water once again to the surface, algae begin to once again proliferate, and the chlorophyll concentration rises, as shown here by that false color image. Now, going back to dynamics, I start off by showing data that's monthly averaged. In the modern era, we can measure with extreme precision. When you start going back into the paleo record, you start now looking at data that has much lower temporal resolution. But it gives you the ability now to look at longer term trends. But here's a really cool study that I found in Geophysical Research Letters 2015. Maya Tolstoy et al. Does a comparison of the Milankovitch cycles against everybody knows that CO2 over the past million years has trended up and down relative to orbital forcings associated with what we call the Milankovitch cycles. What is being brought to bear here is what we refer to as the Southeastern Pacific Rise bathymetry. Bathymetry is just basically the change in deep see ocean bottom elevation as material like lava and sediment, precipitation of dissolved inorganic compounds precipitates out onto the ocean bottom, and that surface will begin to rise, or its bathymetry starts to grow positive over time. And then as that rate drops and bathymetry starts to go negative, it's because those plates have continued to spread and move and drop that elevation over time. So my understanding of what this data shows is, particularly when you look at the power spectrum, all three show a very strong temporal correlation around that 90 to 100,000 year time frame over that 800,000 year time series shown on the left. Most importantly, it shows that when we transition from a deep neoglacial state, the last glacial maximum, that not only did CO2 suddenly rise, but the bathymetry rise in the Eastern Pacific region also rose in step, phase locked in time. I find that hardly coincidental. I do believe that this is basically what occurs when we see all that material accumulated on the ocean bottom. The alphabet soup is being pushed out of elements, is being pushed out of the mid-ocean ridge spreading zone into the deep water. And CO2 off-gassing that we see there, the rising CO2 concentration in the atmosphere around that sudden rise towards a Holocene thermal maximum, is coupled with this lithospheric process, and that it's injecting at the same time that all that tropospheric temperatures, tropospheric CO2, surface warming, there is a geological process that is likewise reawakening from its slumber during the glacial maximum. And it coincides with warmer temperatures and higher CO2 measurements in the atmosphere. So I think, people who like the work of Arthur Wittner, they would probably be inclined to think along the same lines when looking at this data. There's another study that came out just this year that I think is very important for this discussion. And it shows that the Antarctic circumpolar circulation, the largest westerly driven ocean current on the planet, it's likewise seen to show a marked positive transition when the Eastern Pacific rise is starting to activate during the Holocene thermal maximum, and the transition from a deep glacial maximum. We see that the ACC goes positive by a very large percent. You can see here from 40 to 100% variance in that ocean current rate. Now, for people who aren't aware, this oceanic circulation current is driven by the roaring 40s, the most powerful surface wind speed that is coming from the west and moving east on the planet. So like this here in my mind is related to my model, which I showed in the very beginning, where it's showing ocean currents, atmospheric circulation currents are coupled with changes in tropospheric CO2 concentration and changes in lithospheric activity and deep water geochemical exchange with the lithosphere. Here's just a familiar image for showing the role of the ACC in exchanging deep water, surface water with all of the oceans. It's a very large current, and as that last paper I showed suggests, there is a very large range in its estimated value, both currently as well as over paleoclimatological or geological timescales. Here's a quick representation of the time variance since the 1940s to now of the Pacific easterlies. Again, the Pacific easterlies are integral to this topic because they control the rate of deep water upwelling and water circulation. They're coupled. Atmospheric circulation is coupled with overturning of the oceans. It just shows you just how, both on a 12-month average basis in the top and in a 5-year rolling average basis in the bottom, just how much variance there has been since the middle of the 20th century to now. An easterly deceleration again represents an El Nino, surface warming, a decline in upwelling rates, and an acceleration or a more negative trending easterly wind speed represents El Niña. You can see the peak in the 80s, 90s, and the fact that it started to once again accelerate after the mid-90s to present. Here's just something, here's a complementary image that shows the relationship between long-term changes in deep water upwelling and tropical sea surface temperatures in the Pacific. This is from McFadden and Zhang, 2006. And you'll see on the left-hand side, equatorial convergence, that's their upwelling rate in millions of cubic meters per second. You'll see that just how much the rate of upwelling decreased from 28 million cubic meters per second estimated in the early 1960s and early 70s to as low as 12 in the mid-1990s. Now, that mid-1990s mark is an important one. I'm going to get into that a little bit further now. Here's another study that's showing the kinetic energy of the oceans increased markedly around there's a transition around the mid-1990s and really picked up in the early 2000s after the major El Nino of 1998. This year in this study, they showed that it had to do with the transition to a negative PDO state, which is just another way of saying the Pacific easterlies began to accelerate significantly around the mid-1990s. Here's some Arthur Vitero's work. So if I pronounced his name wrong, I think I have.
I think it's Vitorito, maybe?
Vitorito, thank you. Sorry, Arthur, if you're listening. Arthur really points out in his publications that there was a major trend, a major change in mid-ocean spreading zone seismic activity around 1995. You'll see the top figures for global, and then the bottom one just shows it by zone, which areas increased the most. Indian and Atlantic really picked up, Pacific too, but not by near as much, at least in the data he's showing here. Here's my data going back to bringing together the TGR data, which again is the seasonally detrended first derivatives of CO2 at both Mauna Loa and South Pole. Now I'm using the same methods where I take on the Pacific easterly wind speeds. I take the anomaly of the wind speeds, apply the monthly, the seasonal detrending, and apply the first derivative. And what we find here is you can really see it during strong ENSO events that there are significant temporal correlations. Likewise, I find quite interesting is that if you take the average on either side of the 1997, 1998 Super El Nino, but there is about a 40% increase in the TGR after that major 1995 seismic activity uptick that Arthur has pointed out in his work. Here's cross-correlation analysis just to show both South Pole versus Mauna Loa, SP versus ML, and then South Pole versus the Pacific trade wind speed, PTWS. This is where I take and do cross-correlation analysis of the derivative time series on the previous slide, just to show that the peak around tau equals 0 suggests that on average over the time spans that I've shown you, there is no lag. There's no temporal lag between the peak positive values of these first derivatives, and then that's supposed to show that because there's no lag, that at least on a 1 month basis, that the rate that the changes that are occurring in the atmosphere from the time that CO2 is off-gassed in the intertropical convergence zone of the Pacific to the time those gases are transported to these monitoring stations at higher latitudes in either hemisphere, the transport times are very fast. There's no lag. Again, because I say there's no lag because this is 1 month data. So if there's no lag, then that means that the time the off-gassing or the change in the rate of off-gassing is transported and ripples out to higher latitude points, the time scales are faster than 1 month. I hope that I explained that effectively, and hopefully, Tom, if I didn't, you can bring me back to that and I can try again. So we're nearing the end point. Here's just a couple more slides where I'm going to hammer home more just how much the Walker circulation is dominating natural variability, in this case, sea surface temperatures across the entire Pacific Basin. Here's from 2000 to present, showing the anomalies, not the derivatives. This is the anomaly of the Pacific easterly speed. I use anomaly so that it goes positive. So that instead of being inverted, I want the easterlies to have the same direction in terms of change as the Pacific sea surface temperatures. When the Pacific easterlies go positive, that means that you have a deceleration. You're moving towards an El Nino. When they go negative, it means you're accelerating and their speed is picking up and you're moving towards La Ninas. And no surprising, the entire Pacific region shows that its sea surface temperature trends these changes. There are different types of El Ninos. We've got the classic Eastern Pacific El Nino, and we've got our Central Pacific El Ninos that are often referred to as El Nino Madokis. They're different, but also share a lot of similar mechanistic processes. Here's where I do the same comparison. Here is the Pacific easterlies versus the UAH, global air temperature anomaly, showing that when the peak deceleration occurs in your Pacific easterly winds, that's the trigger point for an El Nino to form, that there's a lag, that the global, by the time all that heat is transported up towards higher latitudes, and it impacts the global average, there's a lag between cause and effect. And those values, the lag factors vary across this time span shown, approximately 30 years. But again, I think this, for me, this really is exciting because it highlights just how much of the variability in the global average air temperature is being driven by something that is purely natural. Moving towards the closing mile here. Here is the global air temperature data from UAH shown against the South Pole TGR time series. Now, the TGR, again, is a derivative, and the global air temperature anomaly is an antiderivative. They're not the same thing. But by showing them, juxtaposing them, I'm highlighting what I think should be pretty obvious, which is that they're both changing with a very similar time dependence. The global air temperature is being, on an interannual basis, is being driven by the El Nino Southern Oscillation. El Nino to La Nina transitions. You see that from 1958 to present. Likewise with the global air temperature. Now, going back to my reference that one is a antiderivative, the air temperature, and the other is a derivative, I'm just going to remind people of first year calculus that when you apply a first derivative to an antiderivative, you create a time shift. So here is, I should have maybe used different colors, my apologies. Here on the left-hand side, we have the global air temperature anomaly, the antiderivative. That's the solid red curve. The derivative of that antiderivative is the dashed curve. And its magnitude is on the far right y-axis. So no doubt when you apply a derivative, it's the instantaneous slope of the antiderivative, right? So when you look at the peak to peak for both the first derivative and the antiderivative, there is a 6-month lag. The derivative shifts forward in time. So this derivative is the global air temperature, right? And so going back, if there's a 6-month lag here between the first derivative of the global air temperature from UNH and its antiderivative, then that implies when you go here and you compare derivative to derivative, you would see that the peak rate of change of the global air temperature will be leading the TGR for CO2. And then going back to the mechanisms that I described earlier, the TGR goes positive when you get cooling and upwelling and La Nina. That's why you get a peak TGR. The air temperature peaks when you get the opposite. When an El Nino occurs, upwelling collapses and the easterlies collapse. And so you would expect the air temperature peak to be ahead of the rate of change or the peak in CO2 concentration. I'm not going to read this verbatim, and Tom can make my slide available for people to review. I've tried to outline the underlying hypothesis. The explanations are here shown. I really do believe that I want to convey to our Tom's global audience that I do believe that we need to begin to expand, take into consideration the fact that geochemical exchange rates between deep water, which takes thousands of years to transit the ocean bottom, and the lithosphere is a factor that has to be considered. And that the upwelling signature of the Eastern Pacific on the TGR shows that it's not the Atlantic upwelling zone or the Sea of Oman upwelling zone that is being shown in the TGR for CO2. The cold tongue region is right over the most seismically active spreading zone on the planet. And until I see a recognition of this fact, I have a very hard time accepting the mainstream explanation that the time dependence of the tropospheric CO2 is entirely due to man, and that man is the sole reason behind the positive imbalance that we see with growing CO2 concentration in our atmosphere. Arthur Vitero is onto something, and more people need to be looking at greater depth at this topic. Thank you very much. Tom,
All right.
Thank you.
All right. I wanted to clarify what you're saying, that we're told that the CO2 has risen from maybe 280 parts per million to a little over 420. Based on what you've seen, do you think what % of that has been caused by humans? Any idea?
No, I don't have an idea. There are so many estimates, but an estimate is not a measurement. We do not measure flux rates. You calculate flux rates. We measure concentration or change in concentration, but flux is a function of change in concentration, change in velocity, right? So you have to have two separate measurements, each with their inherent accuracy and errors, to calculate flux. The Earth is huge, 500 million square kilometers. The ocean is 320 million square kilometers. And as I'm showing, atmospheric circulation and oceanic circulation rates are not constant through time. So even if you did a big global survey today, it would be out of date in 10 years. So all I know, Tom, is we are measuring changes in concentration, and that's what the TGR is. It's not a flux rate. It's a change in concentration over time. There's not enough information, I believe, to take that data and convert it into accurate estimates for source and sinks, because there's just too many. We don't know how many termites there are, how many bacteria there are, how many, you know where I'm going with that, right? Plants, everything is always in flux, no pun intended. It's always changing. Sources and sinks are constantly changing. So I hope that helps a little bit.
Yeah, yes, it does. Any comments? I'm just looking at this headline here. What you need to know about record-breaking heat in the Atlantic. Do you have any ideas what's happening there with warmth in the Atlantic right now recently?
Well, I believe that 2023 marked the beginning of that, correct?
I think so.
Yeah, if you look at a monthly average to now, you will find, I believe, that around last summer, around this time, you started to see a rapid uptick. Now, the reason I believe, and the literature is full of this, changes in sea surface temperature between high latitude locations like the North Atlantic are what we call teleconnected to changes that often occur in the tropics, particularly the Pacific tropics. The Pacific tropics seems to be the global trigger. So while we're seeing the North Atlantic rise in, as you're referencing to, Tom, you're also seeing the same lock phase and time rate of change in the tropics, particularly in the Pacific, but it will be in the Pacific, in the Atlantic subtropics and the Indian subtropics as well. So I believe it's just a teleconnection. It's a natural variability and a natural response to what is driving, which is Walker circulation dynamics.
All right. And I think my final question is, one of your last slides, you showed a UAH data kind of stepping up with El Ninos over since 1996. Do you have any thoughts on whether that might step down in coming decades, or what do you think there?
No one, everybody has their models. Most models can't, most ENSO models can't see past the spring barrier, right? They have a hard time predicting is there a 50% chance of getting a La Nina now that we've had an El Nino come October, November? So if we can't see past the spring barrier, how can we see the future past a year, right? So I am of the school of thought that the vast majority of ENSO phenomenon is a subharmonic of the seasonal cycle. there is a school of thought that suggests that El Ninos correspond to changes in the Schwab cycle and higher order solar dynamics. That's a whole other topic to itself. But if that is the case, then we can, in theory, predict where the global tropics are going to go relative to what's happening with the sun. But there's as many of your friends know and say, there's a lot of uncertainty when it comes to the solar dynamics in terms of where it's been and where it's going. So sorry, I can't help. I have no crystal ball.
Nobody does. Okay, any other final points you'd like to make before we finish this one up?
No, other than the fact that feel free, anybody wants to hit me up. I'm pretty active on LinkedIn, Joseph Fournier. You can find me there. I welcome criticism. I welcome opportunities to learn from people who know more than me. And if you want more information, likewise, hit me up. I'd love to talk with you. Thank you very much, Tom, for the invitation. I enjoyed it a lot.
Thank you very much. It's great information. We'll talk to you next time, Joseph Fournier.
Take care.